The Cassini-Huygens mission stands as one of the most remarkable space exploration successes in history. 4 robotic probes have visited Saturn, but Cassini-Huygens truly stands out, both scientifically and literally. Its impact is profound, generating over 4,000 research papers and revealing 6 new moons. Getting to Saturn was an incredible journey. Launched in October 1997, the spacecraft faced immense challenges navigating the Sun's gravitational pull. A rare planetary alignment occurred, happening only once every 600 years, which made the mission possible. Cassini used gravitational assists from Venus and Earth, flying incredibly close, just 100 kilometers above Earth's surface, before getting a final push from Jupiter. The mission's achievements are staggering. Cassini traveled 7 billion kilometers, spending 13 years orbiting Saturn, and gathering unprecedented data about its gravity, magnetosphere, rings, and overall structure. Its scientific contributions were matched by its visual storytelling, capturing jaw-dropping images of Saturn and the solar system. The mission's finale was equally dramatic. Cassini continued collecting data until its very last moments, ultimately plunging into Saturn's atmospheric clouds and breaking into thousands of pieces. This grand finale came after scientists had long been intrigued by Saturn's largest moon, Titan, which was confirmed to have an atmosphere during the Pioneer 11 probe's initial visit in 1979. Today, Cassini's legacy continues through the thousands of research papers and ongoing discoveries stemming from its incredible journey. Its mission represents not just a technological achievement, but a profound exploration of our solar system's mysteries. Cassini's power source was unique and remarkable. The spacecraft relied on 3 radioisotope thermoelectric generators, RTGs, powered by approximately 33 kilos of radioactive plutonium. This radioactive decay provided consistent energy throughout the mission, generating about 700 watts of power until its end. The potential risks of carrying radioactive material were significant. NASA carefully calculated the consequences of a possible crash landing on Earth. In the worst-case scenario, they estimated about 5,000 potential cancer deaths. Despite these concerns, the agency deemed the 1 in a million chance acceptable. RTGs were crucial because solar panel technology couldn't effectively power a spacecraft so far from the Sun. This power source allowed Cassini an extended operational life, ultimately limited only by its propellant supply. The mission had ambitious scientific objectives, including exploring Saturn's rings, moons, magnetosphere, and atmosphere, with special focus on Titan. The Huygens probe, built and operated by the European Space Agency, was a key component of the mission. Measuring just 1.3 meters wide and weighing 300 kilos, it detached from the orbiter and spent 22 days in space before entering Titan's atmosphere. Its primary mission was to collect atmospheric data during a 2.5-hour descent. Interestingly, the probe was designed with the possibility of landing on an ocean or lake in mind. However, it actually touched down on what appeared to be a dried lake bed. With only a brief wake-up timer activated 15 minutes before atmospheric entry, Huygens successfully gathered crucial scientific information about the Titan's atmospheric pressure, composition, and wind speeds. The scientists' careful planning and innovative technology allowed this remarkable mission to push the boundaries of our understanding of Saturn and its complex system of moons and rings. Ingenieurien und Cassini's mission has been nothing short of remarkable. Over 13 years, the spacecraft captured extraordinary images of space, particularly stunning views of Saturn and its moons. Dedicated researchers have meticulously processed over 1 million photos to provide unprecedented perspectives that feel like sitting directly on the spacecraft. As Cassini's fuel supply dwindled, scientists strategized to maximize their remaining research opportunities. They devised an ambitious plan to explore Saturn more intimately than ever before. Starting November 30th, 2016, the spacecraft began an extraordinary series of maneuvers, repeatedly climbing above Saturn's North Pole and diving near its intricate ring system. By April 22nd, 2017, Cassini embarked on its most daring phase, the grand finale. This series of increasingly risky orbits brought the probe closer to Saturn than any previous mission, ultimately leading to its deliberate destruction. NASA's objective was to extract every possible scientific insight before the spacecraft's inevitable end. During these final orbits, Cassini accomplished extraordinary scientific goals. It collected detailed measurements of Saturn's gravity and magnetic fields, potentially resolving long-standing mysteries about the planet's internal rotation. The mission's particle detectors analyzed ring particles, while cameras captured ultra-close images of Saturn's clouds and rings. These unprecedented observations will significantly enhance our understanding of giant planetary systems. No previous mission has explored Saturn's inner regions with such precision. The data collected promises to reveal insights about planetary formation, ring dynamics, and the complex interactions within this remarkable planetary system. Importantly, all images are real, simply color-corrected and enhanced to showcase movement, with absolutely no computer-generated imagery involved. Cassini's journey represents a triumph of human exploration and scientific curiosity. Ancient families of planets form and evolve, and for Cassini, its final orbit would be a dramatic conclusion. As the spacecraft neared its end, it would fall into Saturn's atmosphere, completing its remarkable 20-year mission with a crucial final act. The mission's last moments were designed to protect two biologically interesting worlds, Enceladus and Titan. NASA ensured that no hardy microbes could potentially contaminate these pristine environments. By trading Cassini's longevity for an unprecedented close encounter with Saturn, the mission team made a strategic decision that was easy to justify. The spacecraft was already running out of fuel. During its grand finale, Cassini was given the go-ahead to dart between Saturn's rings, offering a unique perspective never seen before. The spacecraft captured extraordinary views of Saturn's moons, revealing fascinating details about these celestial bodies. The shepherd moons were particularly intriguing. Atlas, a 40 kilometers wide moon near the A-ring's outskirts, appeared remarkably smooth, with an absence of impact craters. Ring dust collected around its equator, creating a distinctive shape. Similarly, Pan, a 30 kilometer wide moon in the Encke Gap, sweeps up stray ring particles, maintaining the gap's steady structure. Another tiny moon, just 8 kilometers in diameter, resides in the Keeler Gap of the A-ring. Despite its weak gravity, this small body creates mesmerizing effects. As it orbits, it whisks nearby dust particles, generating waves and ripples in the rings. These dynamic movements create side-to-side and up and down motions, visible through the shadows they cast. The mission's final approach was both inspiring and romantic, a fitting conclusion to a thrilling story of discovery. Watching waves follow the moon's orbital path against the backdrop of glorious Saturn and its many moons would be a breathtaking sight. The Cassini mission captured incredible images during its grand finale, with one particularly striking photograph showcasing the Janus 21 spiral density wave in Saturn's rings. What might look like multiple separate rings is actually a complex phenomenon similar to how spiral galaxies form. In reality, the image reveals just two tightly wound spiral arms looping multiple times around Saturn's ring plane. Every alternate line in the image belongs to the same spiral arm, creating an intricate visual pattern. The photo appears tilted at the top left, but this is an illusion caused by how density waves propagate from the central plane. The wave's complexity deepens when considering the orbital dynamics of moons Janus and Epimetheus. These two moons switch positions every 4 years, and each switch triggers a response in the rings, creating new wave crests. NASA notes that the distance between wave crests represents 4 years of wave propagation, effectively encoding decades of orbital history. Intriguingly, the uppermost left part of the image corresponds to the Moon's positions during the Voyager flybys in 1980 and 1981, the period when Janus and Epimetheus were first confirmed as distinct objects. This encoding is reminiscent of tree rings, marking years of growth. Beyond this spectacular image, Cassini also captured other fascinating ring features, such as small propeller-like structures scattered across different ring locations. Scientists often photograph both illuminated and unlit sides of the rings to compare and analyze details, even though the image scale is tiny, around 500 meters per pixel. These images reveal intricate connections, showing how small moonlets are physically linked to ring materials through bands that might be barely visible, but are scientifically significant. The mission's ability to capture such detailed insights makes these observations truly remarkable. And Cassini's final mission captured extraordinary details about Saturn's rings and atmosphere. Several moonlets were discovered near the Anchor Gap, with none believed to be larger than 2 kilometers and likely having a snowball-like density. The spacecraft observed tiny solid objects around the rings, created by gravitational interactions from shepherd moons. These objects survived multiple encounters with the rings, kicking out dust and particles that sometimes traced their orbital paths. While the objects themselves remained invisible, due to dust obscuring the view, their impact was clearly visible. Saturn's northern hemisphere was experiencing full summer during Cassini's flyby, revealing its famous hexagonal polar structure. At the hexagon's center, a permanent polar vortex housed a massive hurricane. The pole's color was changing seasonally, noticeably different from its darker appearance in 2012. Multiple storms dotted the planet's surface, with bands reminiscent of Jupiter, though less vivid in natural light. Cassini's proximity allowed detailed observations of the planet's horizon, including atmospheric stratospheric haze that shifted across the image. Scientists were particularly interested in the atmosphere's composition. Although they anticipated Cassini would not survive its final atmospheric approach, the spacecraft was programmed to collect critical data before burning up. 1 week before its atmospheric entry, Cassini continued capturing images. The mission produced remarkable time-lapse visualizations, splicing countless individual images to simulate flying alongside the spacecraft during its ultimate journey. These sequences, starting from September 8th, 2017, provided unprecedented insights into Saturn's complex and beautiful environment. Here's the rewritten version. During its mission, Cassini focused intently on Enceladus, a moon considered one of the solar system's prime candidates for potential life. Just 1 week before the mission's end, the spacecraft had already made remarkable discoveries about this fascinating celestial body. Over 100 water plumes were detected, erupting through Enceladus's crust, originating from a subsurface ocean. These water emissions freeze in space and have created the stunning, tenuous E-ring around Saturn. This ring is so delicate, it's only visible when backlit by sunlight, and might be the most naturally occurring object in our solar system. A remarkable time-lapse captured by Cassini on September 11th revealed these moon's plumes in extraordinary detail. The spacecraft was positioned at the furthest point of its final orbit, providing a natural light mosaic that showcased unique astronomical features. Saturn's rings, D, C, B, A, and F, were clearly visible, with the planet's short shadow cast across them. At this time, Saturn's northern hemisphere was experiencing summer, allowing a clear view of its famous hexagon storm. Subtle bands could be detected in natural light, but the most intriguing aspect was the night side's dim illumination. Light reflecting off the rings meant that the hemisphere facing away from the sun wasn't completely dark. As Cassini approached Saturn on September 12th, it captured atmospheric images near the planet's terminator line. The low-angle sunlight revealed massive cloud structures casting shadows, stretching kilometers across. The scene, approximately 5,500 kilometers wide, could easily accommodate Saturn's moon type. By September 13th, Cassini's final observations included intricate details of orbital interactions. Keen observers might notice ripples both in front of and behind certain moons. These ripples result from differing orbital speeds. Inner rings move faster, while outer rings travel more slowly, creating complex gravitational interactions that expose ring material in fascinating patterns. Not on and on. Its final day, Cassini captured some incredible views. During a last look around the Saturn system, it focused on Titan, a moon that had been a key subject throughout its mission. The spacecraft also glimpsed Saturn's rings, with the uneven F-ring barely visible at the bottom of the image. As Saturn grew larger in view, Cassini spent 40 minutes observing Enceladus before disappearing behind the planet's limb. The final image was of the region where it would ultimately plunge into the atmosphere. It was nighttime, with Saturn illuminated by light reflected off its rings. The photos weren't a priority for scientists. Despite their beauty, they would consume valuable bandwidth, and the team wanted to collect every bit of data in real time before the spacecraft's destruction. This was a unique opportunity. Humans had never before directly probed Saturn's atmosphere. When Cassini entered the tenuous outer layers, it was traveling at 123,000 kilometers per hour. Its remaining fuel was used by thrusters to keep the antenna pointed toward Earth. Just 1,900 kilometers above Saturn's clouds, the thrusters fired at maximum capacity to prevent the spacecraft from spinning out of control. Cassini was directly sampling the atmosphere, which was simultaneously heating the spacecraft. Within seconds, the thrusters were overwhelmed, and the craft began to tumble, cutting off communication with Earth. Its onboard computers would have been trying to diagnose the problem, with gyroscopes and star trackers indicating the spin. Approximately a minute later, the spacecraft disintegrated completely, burning up in Saturn's atmosphere. When data finally reached Earth about 90 minutes later, scientists considered the mission's final moments a tremendous success. Cassini had recorded critical information about Saturn's atmosphere, ionosphere, dust particles, and magnetic fields. The most remarkable aspect of the Cassini mission is its ongoing scientific contribution. Years after its dramatic end, researchers continue to analyze and re-examine the collected data, uncovering new insights about Saturn. The mission truly keeps on giving, with scientific papers and discoveries still emerging from its wealth of information. And Saturn is a world of mysteries, challenging everything we thought we knew about planetary science. The second largest planet in our solar system, it stands out with its iconic rings and distinctive hazy yellow surface. Its uniqueness goes far beyond mere appearance. The Cassini probe spent 13 years circling the planet, collecting unprecedented data that has both illuminated and deepened our understanding. This mission revealed phenomena that defy conventional scientific models, from temperature variations to complex magnetospheric behaviors. One striking example is the massive hexagonal storm at Saturn's North Pole. Spanning 29,000 kilometers, wide enough to comfortably contain Earth, this storm remains fixed in longitude, unlike other cloud systems that swirl at speeds up to 1,800 kilometers per hour. Scientists still struggle to fully explain its behavior, though laboratory experiments have created similar hexagonal patterns on smaller scales. Even basic questions remain unanswered. Determining the length of a day on Saturn has proven surprisingly complex. Its thick cloud cover obscures any potential landmark reference points, and these clouds move at different speeds relative to the planet's core. The rings themselves orbit at varying velocities, further complicating measurements. As researchers continue analyzing Cassini's mountains of data, more mysteries emerge. Each discovery seems to raise more questions than answers, highlighting Saturn's status as a truly enigmatic world. Its behavior continues to challenge scientific understanding, making it one of the most fascinating planets in our solar system. Despite decades of observation, Saturn remains an astronomical puzzle, a testament to the incredible complexity of planetary systems and the limits of our current scientific knowledge. Scientists have developed clever techniques to determine the rotation of gas giants by examining their magnetic fields. They hoped this method could work on Saturn, even though planets generate these fields through a specific process. The dynamo effect occurs when a planet rotates, causing liquid metal in its core to spin and shift. This massive molecular motion creates powerful energy currents that produce magnetic fields. Typically, a planet's magnetic pole is slightly offset from its rotational axis, a critical feature that ensures the field's stability. Detecting the magnetic field's movement around a planet's true axis can reveal its day length. The Cassini mission was equipped to track these shifts. However, Saturn defies expectations. Its magnetic pole is almost perfectly aligned with its rotational axis, accurate to within 0.1 degrees, something that should be impossible according to dynamo theory. Saturn's magnetic field is remarkably powerful, measuring 580 times stronger than Earth's and significantly influencing the entire planetary system. Scientists remain puzzled by its origin. The standard planetary dynamo model fails to explain this phenomenon, leaving researchers uncertain whether another atmospheric effect is warping the magnetic field, or if an entirely new magnetic field generation method exists. Radiation provided additional insights. Saturn is an electrically active system with charged ions, moving between atmospheric layers and rings. Radio waves emitted by these magnetic interactions fluctuated in a pattern suggesting planetary rotation. Based on these radio wave measurements, scientists initially estimated Saturn's day length at 10 hours, 39 minutes, and 23 seconds using Voyager data. They hoped the Cassini mission would further refine this measurement, offering a more precise understanding of the planet's rotational characteristics. Throughout its 13-year mission, Cassini discovered some puzzling phenomena around Saturn that challenged scientists' understanding of planetary behavior. The spacecraft's measurements revealed subtle shifts in the planet's rotation speed, drifting about 1% annually, sometimes rising and sometimes falling. This variation seemed to suggest the planet was changing its own rotation, which should be impossible for a massive body like Saturn. Scientists quickly ruled out actual rotational changes, concluding that some external effect was distorting their measurements. They suspected atmospheric interactions were creating interference, essentially cloaking the planet's true rotational characteristics. Saturn's magnetic field and auroras presented another intriguing mystery. Unlike Earth's auroras, which result from solar-wind interactions, Cassini detected auroral activity that occurred independently of solar-wind conditions. This suggested non-solar origins and hinted at unknown processes within the planet. Even more fascinating was Saturn's heat profile. The planet radiates about twice as much energy as it receives from the Sun. While some heat could be explained by gravitational compression, additional mechanisms were needed to fully understand this phenomenon. The key might lie in Saturn's complex atmospheric structure. As a gas giant composed primarily of hydrogen and helium, the planet's interior undergoes extreme transformations. Deep within the atmosphere, intense heat and pressure potentially convert gaseous hydrogen into liquid metal. Some scientists even theorize that hydrogen might become so compressed it forms diamond-like structures that rain into the planet's depths. The auroras themselves might be generating significant heat. Electrically charged particles from Saturn's rings and moons potentially create powerful thermal interactions. Where warm and cold atmospheric zones meet, intense winds emerge, driving complex planetary dynamics that continue to intrigue researchers. Saturn's day length turned out to be hidden within its rings, solving at least one mystery surrounding the planet. By carefully measuring the ripples caused by gravitational variations, scientists discovered the precise rotation period: 10 hours, 33 minutes, and 38 seconds. Electrical winds and charged ions swirling through Saturn's upper atmosphere might explain the strange data scientists have been analyzing. These currents potentially skew radiation measurements and could account for why the planet's magnetic fields appear misaligned from expectations. The complex motion might stem from a conductive layer within Saturn's clouds moving at a different speed, generating its own magnetic fields. However, many of these explanations remain unproven, leaving scientists eager for more definitive answers. NASA's next mission to Saturn, launching in 2027 with the Dragonfly spacecraft, will provide additional insights. While primarily focused on exploring Titan, Saturn's largest moon, this mission might help unravel some of the planet's persistent mysteries. Titan itself is intriguing, being the most Earth-like object in our solar system. It possesses a nitrogen-rich atmosphere similar to Earth's, complete with rain cycles and liquid lakes, though these are composed of methane rather than water. This unique characteristic makes it a compelling target for scientific investigation. Despite ongoing research, many of Saturn's deepest secrets remain unresolved. the planet continues to breathe its complex winds, potentially holding the key to understanding its intricate systemic balance. Scientists remain hopeful that future missions will gradually unveil the planet's enigmatic nature. Sun and Saturn's rings are younger than many might expect. While the planet could be over 4 billion years old, scientific evidence suggests these stunning rings may have formed only within the last 100 million years. Moreover, they are gradually disintegrating, potentially disappearing entirely in another 100 million years. These magnetic fields and gravitational forces keep the rings precisely aligned, creating a mesmerizing cosmic display. Though the potential loss of these rings might seem melancholy, there's an unexpected sense of fortune in witnessing this ephemeral beauty. Had humanity arrived at a different moment in cosmic time, we might have missed this extraordinary celestial spectacle. The incredible Cassini mission revealed unprecedented scientific insights and visual wonders, capturing the enigmatic nature of Saturn in ways previously unimaginable. Jupiter, another fascinating planetary marvel, presents a different yet equally compelling narrative. Located between Mars and Saturn, approximately 778 million kilometers from the Sun, this massive planet completes an orbit every 12 Earth years. Its axial tilt of just 3 degrees means minimal seasonal variation. As the largest planet in our solar system, Jupiter's significance extends far beyond its size. Its mass represents almost 1,000th of the Sun's mass, seemingly small, yet substantial, when considering the Sun contains 99.86% of the solar system's total mass. In fact, Jupiter's mass equals nearly 2.5 times the combined mass of all other planets. A powerhouse of colossal storms and intense radiation, Jupiter has become a focal point of scientific exploration. With 7 flybys, 2 operational orbiters, and additional planned missions, researchers are continually uncovering its mysteries. From understanding its distinctive red coloration to investigating what lies beneath its obscuring clouds, Jupiter holds a vital role in our solar system's dynamics. The planet's scientific intrigue is matched only by its raw, captivating beauty, a testament to the incredible wonders awaiting our discovery in the vast cosmic landscape. The dance between Jupiter and the Sun reveals a fascinating gravitational phenomenon. Most people don't realize that smaller objects can significantly influence larger ones during orbital interactions. While typically this effect seems negligible, Jupiter stands out as a remarkable exception. At the heart of this interaction is the Baryk center, the precise point where 2 orbiting objects balance each other's gravitational pull. In the case of Jupiter and the Sun, this center actually exists above the Sun's surface, about 1.68 solar radii from its center. Think of it like balancing objects on a long stick. The heavier object pulls the center of mass closer to itself. With Jupiter and the Sun, they essentially swing around this shared gravitational point, creating an intricate celestial ballet. Jupiter's influence stems from its massive size. While it isn't the densest planet, it is by far the most massive in our solar system. Its diameter is 11 times that of Earth, and its total mass is 318 times greater. This translates to tremendous gravitational power, over twice Earth's gravity at its surface. This immense gravitational force makes Jupiter a solar system game-changer. Scientists believe it has destroyed numerous celestial objects and prevented planet formation in the ancient past. Its gravity is so significant that it could potentially alter Mercury's orbit over billions of years, potentially causing inner planets to crash into the Sun or be ejected completely. Moreover, Jupiter acts like a cosmic vacuum, protecting the inner planets by absorbing or deflecting dangerous asteroids. It has captured at least 67 moons and continues to play a crucial role in maintaining our solar system's delicate balance. If Neptune were Jupiter's size, or Jupiter were Earth's size, the gravitational dynamics would change dramatically. Mass fundamentally determines gravitational influence, and Jupiter exemplifies this principle perfectly in our solar system. Inzi and Jupiter is the fifth planet from the Sun, positioned 5 times further away from Earth. It stands out as the third brightest object in the night sky, trailing only behind the Moon and Venus. Even with a simple handycam, you can easily observe Jupiter, which reaches a maximum magnitude of -2.94. The planet's appearance is defined by its remarkable cloud layers, which are only about 50 kilometers thick, and contain ammonia crystals similar to those found on Saturn. What makes Jupiter truly fascinating are its spectacular multicolored bands, created by compounds heating up from deep within the planet and rising to interact with the sun's UV light. These compounds, known as chromophores, generate the vibrant patterns we see. Jupiter's surface is dynamic, with colors and patterns changing dramatically over time. While the actual latitude of these bands remains consistent enough to be given identifying designations, their width can vary. The intersections of these bands create numerous storms and turbulence, which drive one of the planet's most famous features, the Great Red Spot. This enormous storm is so large it could easily contain Earth's entire diameter. Discovered in the 17th century, the Great Red Spot might be a permanent planetary feature, though it has notably decreased in size over time. Its color is intriguingly variable, ranging from brick red to almost white. The most recent theory suggests that UV light breaks down chemical compounds, similar to processes occurring elsewhere on the planet. The storm sits higher in the atmosphere than surrounding clouds, allowing it to interact more directly with sunlight. This positioning explains its intense coloration. Jupiter isn't limited to just one remarkable storm. Another notable formation is the Red Spot Junior, which formed between 1998 and 2000, when 3 storms merged and has so far remained unaffected by its larger neighbor. Long-period comets can be influenced by Jupiter, with the planet potentially perturbing their orbits enough to propel them out of the solar system entirely. Amateur astronomers particularly appreciate Jupiter as a target, as recent improvements in consumer telescopes have made detailed observations possible, right from one's backyard. Injan and Jupiter is a remarkable planet with complex inner workings. Its composition is primarily hydrogen, making up about 90%, with helium comprising another 10%, and trace amounts of methane and ammonia. Unlike solid planets, Jupiter's rotation is unique. It completes a full rotation in just 10 hours, but different parts of the planet rotate at slightly different speeds. The poles take 5 minutes longer to complete a rotation compared to the equator. Deep within the planet, extreme pressures transform hydrogen into fascinating states, starting with gases, then liquid, and eventually metallic forms as you move toward the planet's core. These conditions are impossible to replicate on Earth. Beneath these layers lies a rocky or icy core. Despite its massive size, Jupiter falls short of becoming a star. It would need to be about 75 times more massive to initiate nuclear fusion. The planet boasts some incredible features. Its magnetosphere is extraordinarily powerful, 14 times stronger than Earth's, making it the strongest among planets in our solar system. This magnetic field creates stunning effects, like channeling solar wind to the poles and generating magnificent auroras. Additionally, Jupiter's 4 largest moons are shielded from solar wind by orbiting within this magnetic environment. Jupiter also has rings, though they're far less dramatic than Saturn's. The main ring is thin, but bright, stretching about 6,000 km wide. The most distinctive feature is the Metis notch. An interesting childhood curiosity about whether Jupiter could be set on fire is quickly dispelled by scientific understanding. There's barely any oxygen, and stars don't simply ignite like a matchstick. While Jupiter's volume isn't far from the smallest known red dwarf star, it remains a planet, a massive, complex, and fascinating world spinning in our solar system. Jupiter's massive magnetic field seems to provide protection for its moons, but this doesn't guarantee their safety from radiation. The planet hosts an incredibly powerful radiation band that has proven destructive to any probe attempting to pass through it. Take Io, the closest large moon to Jupiter, which experiences an astounding 3,600 RAM of radiation per day on its surface. To put this into perspective, a human exposed to such radiation levels would not survive more than 4 hours. Clearly, these moons are far from being an ideal home. Jupiter boasts 67 known natural satellites, with 51 being less than 10 kilometers in diameter. However, the Galilean moons stand out as some of the most significant in our solar system. These 4 moons, Io, Europa, Ganymede, and Callisto, each have unique characteristics. Notably, Ganymede is the largest moon in our solar system, even surpassing Mercury in diameter. When viewed through an infrared lens, Jupiter's immense size and power become truly apparent. An interesting aspect of the planet is its protective role in our solar system. A space object impact that struck Jupiter could have potentially destroyed Earth had it been directed differently. We can appreciate Jupiter not just for its beauty, but for its crucial function in protecting our planetary neighborhood. The bottom of the planet bears evidence of a massive impact, a stark reminder of the violent potential of cosmic collisions. Jupiter serves as more than just a stunning celestial body. It's a guardian that helps maintain the delicate balance of our solar system. Uranus, the 7th planet from the Sun, orbits an average of 19.2 astronomical units away, more than 19 times farther from the Sun than Earth. Its distance varies by 1.8 astronomical units throughout its year, the largest variation of any planet. This extreme distance makes Uranus incredibly cold, reaching temperatures of 222 degrees C, effectively making it the coldest planet in our solar system. A single year on Uranus lasts 84 Earth years. Its discovery involved an interesting scientific journey. Astronomers initially struggled to predict its orbit, eventually realizing another planet was influencing its path. By mathematically calculating this planet's location, they discovered Neptune. A similar theory now surrounds the potential Planet X, or Planet 9. Some solar system objects aren't where they're expected to be, suggesting another unknown gravitational influence. What truly sets Uranus apart is its unique rotation. Unlike most planets that spin like a top, Uranus has essentially fallen over, rolling along its orbit with an axial tilt of 97 degrees. This creates extraordinary seasonal variations. During solstices, one hemisphere constantly faces the sun while the other remains in complete darkness. Near the equator, only a narrow strip experiences anything resembling a normal day-night cycle, with the Sun barely rising above the horizon. The poles experience even more extreme conditions. 42 years of continuous darkness followed by 42 years of continuous daylight. Currently past its equinox, which occurred in 2007, Uranus rotates every 17 hours and 14 minutes. However, its non-solid surface means different atmospheric sections rotate at varying speeds. Some areas can complete a full rotation in just 14 hours. Remarkably, Uranus is the only planet receiving more solar energy at its poles than its equator. Yet, paradoxically, its equator remains hotter than its poles, another of the planet's many mysteries. Uranus is a peculiar planet with an unusual rotation, likely caused by a massive Earth-sized collision that knocked it sideways. Despite being the least massive of the gas giants at 14.5 Earth masses compared to Neptune's 17, its diameter is slightly larger at 50,7 kilometers. The planet's gravity is surprisingly Earth-like at 7.8 moments squared, which would feel quite comfortable. Its structure is complex, with a rocky silicate core just smaller than Earth, surrounded by a mantle of water, ammonia, and methane ices. Though this mantle is actually an incredibly hot liquid ocean, reaching almost 5,000 degrees. Calling Uranus a gas giant is somewhat misleading. Its atmosphere is extremely thin, weighing only 0.5 Earth masses, with most of the planet's mass concentrated in its core and mantle. This atmosphere consists primarily of helium and hydrogen, with 2.3% methane giving the planet its distinctive aquamarine color. Fascinatingly, some scientific models suggest that the extreme pressure at the mantle's base could break methane molecules, compressing carbon atoms into diamonds. These diamonds might rain through the mantle-like hailstones, potentially forming a liquid diamond layer with solid diamond burgers floating within. Like other large planets, Uranus has a ring system, 13 dark, young rings, mostly just a few kilometers wide. Estimated to be only 600 million years old, these rings are composed of tiny particles made of water ice and dark radiation-processed organics. They're incredibly dark, with an albedo lower than wet soil. These rings are thought to result from high-impact collisions with moons, though the exact mechanism remains unclear. Their composition and origin continue to intrigue planetary scientists, offering a glimpse into the complex dynamics of our solar system's outer planets. Saturn Uranus has rings that are typically held in place by shepherd moons, though this explanation truly applies to only one of the rings. Scientists discovered Uranus had rings in 1977 during a star occultation, where the star's light dimmed several times as Uranus passed in front of it, confirming the ring's existence. Spacecraft have rarely visited Uranus, with Voyager 2 being the only mission in 1986. This spacecraft revealed numerous details about Uranus's ring and moon system, providing close-up images that expanded our understanding. Initially, Voyager brought the known ring count to 11, but later, the Hubble Space Telescope discovered 2 additional rings. The outermost ring was found to be twice as far from Uranus as previously thought. Uranus boasts 27 known moons, categorized into 3 groups: 13 inner moons, 5 major moons, and 9 irregular moons. The inner moons are closely connected to the ring system and might have contributed to the ring's materials. Puck, the largest inner moon, measures just 162 kilometers in diameter and was the only inner moon captured in detail by Voyager 2. These inner moons exhibit fascinating dynamics, constantly disrupting each other in an unstable system. Experts suggest there's a significant possibility of future collisions. The 5 major moons, Miranda, Ariel, Umbriel, Titania, and Oberon vary in composition. Titania stands as the largest, being the 8th largest moon in the solar system at 1,600 kilometers. Most of these moons appear very dark, with Umbriel being the darkest. While Miranda consists mainly of water ice, the others are thought to contain a mix of water and rocky materials. They might have differentiated interiors, potentially featuring a rocky core, an ice mantle, and possibly even a liquid water ocean layer. An intriguing characteristic of these moons is their axial tilt, which matches Uranus's. During solstice, an observer would see the sun moving in a circular path, never setting, with only one side of the moon facing the sun. The 9 irregular moons, likely captured objects, orbit much further out than the major moons. They range in size from 20 km to about 200 km, with Pyoxus being the largest of this group. Montan Uranus has some of the most unusual characteristics in our solar system, especially when it comes to its climate and magnetic properties. Telescope technology has only recently allowed scientists to gain detailed insights into its surface, making definitive statements about changes between Uranian years challenging. As the planet approaches its solstice, a notable phenomenon occurs. The pole begins to brighten, and a distinct colour forms. Moving away from the solstice, both the pole and colour start to dim. Researchers believe this brightness is related to thickening methane clouds, though the exact cause remains unclear. Seasonal changes also impact the planet's atmospheric conditions. Storms on Uranus are relatively rare compared to other gas giants, but they are thought to be influenced by seasonal variations. Improvements in telescope technology have revealed bands stretching around the planet, similar to other gas planets, though these are primarily visible in infrared light. One of the most intriguing aspects of Uranus is its unusual magnetosphere. Unlike most planets, its magnetic field does not originate from the geometric center and is not aligned with the rotational axis. Instead, it is offset by 59 degrees, creating a significantly stronger magnetic field at the North Pole compared to the South Pole. Theories about this unique magnetic configuration range from the possibility of a liquid diamond ocean deflecting the magnetosphere to the suggestion that it might be the liquid mantle rather than the core, producing the magnetic field. The magnetosphere is approximately as strong as Earth's, and due to the planet's unusual rotation, its magnetotail corkscrews millions of kilometers into space. The magnetic and atmospheric peculiarities make Uranus a fascinating subject of study, highlighting the complexity and diversity of planetary systems in our solar system. When astronomers first discovered Uranus, they noticed something odd about its orbit. The planet wasn't behaving as expected, according to their models. In 1846, astronomer Urbain Le Verrier made a remarkable prediction. There must be another undiscovered planet. He calculated exactly where this unknown planet should be located. Johann Galle took up the challenge and found the planet almost precisely where Le Verrier predicted, just a degree away from the calculated point. Shortly after, Neptune's largest moon, Triton, was also discovered. For decades, Neptune remained a mystery. Its vast distance from Earth and tiny apparent size made ground-based telescope observations incredibly challenging. Everything changed in 1989 when Voyager 2 arrived, suddenly revealing massive amounts of information about the planet. We could finally see what Neptune actually looked like, confirm its planetary rings, and discover numerous previously unknown moons. Today, Neptune holds the title of the 8th and furthest planet from the Sun. It orbits at 30 astronomical units from the Sun, equivalent to 4.5 billion kilometers. At this immense distance, a space probe would take about 13 years to reach the planet. Its extraordinary orbital period means a single Neptunian year spans 165 years, so we've only witnessed one complete orbit since its discovery. The planet's extreme distance results in incredibly cold atmospheric temperatures, averaging around 201 degrees C. Its axial tilt of 28 degrees is remarkably similar to Earth and Mars, which means Neptune experiences seasons comparable to our own. The key difference is that each season on Neptune lasts approximately 40 Earth years. Currently, Neptune's southern hemisphere is in spring. During this season, it receives more sunlight and appears notably brighter, a fascinating phenomenon considering the Sun is 900 times dimmer at Neptune's distance. Despite this reduced light, the increased solar radiation still makes a significant impact. The southern hemisphere warms up by about 10 degrees C, which releases frozen methane into the stratosphere and contributes to the planet's increased brightness. Neptune is a fascinating planet with some unique atmospheric characteristics. It stands out in our solar system for its incredibly fast wind speeds, reaching up to 260 km/h near the equator, almost at supersonic levels. Most winds on the planet actually travel in a direction opposite to the planet's rotation. The planet's atmospheric layers include the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. When Voyager 2 passed by in 1989, it captured remarkable images of massive storms. The Great Dark Spot, a storm roughly the size of Earth, dominated the planetary landscape, accompanied by a smaller storm south of this massive system. Interestingly, these storms are not permanent. The Hubble Space Telescope revealed that storms which were present in 1989 had completely disappeared by 1999, with new storms continually forming and dissipating. Bright high-altitude clouds also appear and vanish regularly. Unlike Uranus, which has similar composition and size, Neptune experiences much more extreme weather. While Uranus has wind speeds around 900 kilometers, Neptune's are significantly faster. Scientists believe this difference might be related to the planet's internal heat. Though Neptune is the furthest planet from the Sun, it's not the coldest. That title belongs to Uranus. Neptune actually radiates significant internal heat, which could be connected to its active atmospheric conditions. Some astronomers theorize that this might be due to past planetary collisions that generated internal energy. Compositionally, Neptune's atmosphere is primarily hydrogen, 80%, and helium, 19%, with trace amounts of methane. This methane is responsible for the planet's distinctive blue coloration, though darker than you might expect. Neptune's core is surrounded by a liquid mantle of water, ammonia, and methane, where extreme pressures may transform methane into something extraordinary. Scientists theorize that under these immense conditions, around 7 million times Earth's atmospheric pressure, carbon might create unique structures. The most fascinating possibility involves diamonds, not as we typically imagine them, but potentially forming a liquid carbon ocean with solid diamond fragments floating and raining through the mantle. While this remains theoretical, recent technological advances have begun simulating these intense core conditions. Neptune's magnetic field presents another intriguing phenomenon. Unlike most planets, its magnetic field is dramatically offset 47 degrees from its rotational axis. Initially, researchers wondered if this related to axial tilt. but discovering similar characteristics in Uranus challenged that hypothesis. Current theories suggest the magnetic field might be generated by an electrically conducting liquid mantle or deflected through it. This magnetic peculiarity isn't unique to Neptune. Earth's magnetic north also differs from its geographical pole. However, Uranus and Neptune stand out with their extremely tilted magnetospheres. Neptune's auroras offer another distinctive feature. Extremely faint due to reduced solar particle charging and magnetosphere orientation, these Type B or SR arcs differ from typical auroral displays. They sprawl across mid-latitudes rather than concentrating near the poles, potentially spanning entire skies invisibly. Completing the planet's mysterious profile, Neptune possesses a ring system, incredibly dark and sparse. So delicate and distant from the Sun, these rings would be nearly impossible to detect against space's black expanse. There are 5 known rings around Neptune, each named after people involved in its discovery and research. The innermost ring is incredibly faint and wide, stretching about 2 per 1,000 kilometers across. The first bright ring is called Leia. Despite its brightness, it's only 130 kilometers wide. Next to it and connected is the Lasso ring, a very faint band spanning 4,000 kilometers. On the edge of the Lasso ring sits the Arago ring. It's slightly brighter than the Lasso ring and less than 100 kilometers wide. The outermost and most researched ring is the Adams ring. Though only 35 kilometers wide, it's one of the brightest rings. What makes the Adams ring particularly interesting are its bright arcs. These arcs have remained stable since their discovery in 1980, which is unusual because planetary rings are typically uniform. Scientists believe this suggests material clustering within the ring, though the exact reason remains unknown. Neptune boasts 14 known moons, all named after water deities from Greek mythology. Triton stands out as the largest and most massive moon. Its appearance is striking, a burnt orange colour with fascinating patterns. What makes Triton truly unique is its retrograde orbit and its inclination relative to Neptune's rotation, suggesting it was likely captured rather than formed alongside the planet. Triton might even be responsible for Neptune's rings. Its arrival could have disrupted existing moon orbits, causing collisions that broke them into the ring debris we see today. Impressively, Triton is even larger than Pluto and has a tenuous atmosphere. During Voyager 2's flyby, faint clouds were even observed. The next significant moon is Proteus, which is unusually irregular in shape. Typically, such irregular forms are seen in smaller objects like asteroids. At 400 kilometers across, Proteus is larger than Saturn's spherical moon, Mimas. Its non-spherical shape results from past collisions, leaving massive craters. Some of Neptune's inner moons orbit around the rings, acting as shepherd moons. The outer irregular moons are likely captured, with some orbiting prograde and others retrograde. The outermost moons, Sam and Netho, are the most distant satellites known in our solar system. They take an incredible 25 years to complete a single orbit around Neptune, highlighting the planet's immense scale. Neptune's vast hill sphere showcases a unique gravitational phenomenon. When a planet sits far from the Sun, its own gravitational pull becomes dominant in its local space. In Neptune's case, this means the planet exerts substantial control over its surrounding region. The distance from the Sun plays a crucial role in this gravitational dynamic. Because Neptune is so far out in the solar system, the Sun's gravitational influence weakens significantly. This allows Neptune's gravity to create a much larger sphere of gravitational influence compared to closer planets, like Jupiter. Our ongoing exploration of the solar system continues to reveal fascinating details about planetary mechanics. Each planet tells a different story about how gravity and distance interact in space. Researchers are constantly uncovering new insights about these planetary characteristics. We're eager to hear what planetary mysteries intrigue you most. As we work through our solar system series, your feedback helps guide our next investigations. Which planet would you like us to explore in depth? Share your thoughts in the comments and stay tuned for more astronomical discoveries. And our team of astronauts continues to explore the vast reaches of space. Check out the playlist for more astronomy content. I'll catch you next time on our cosmic journey. Sen.